Hi, everybody. Here we are with section 2.2, and this is the indicator of a product. So we learned about the phi function. That's all the numbers that are relatively prime to p. Now we want to know about um, the phi function of a product. So um, so here's the big formula. If u and v are relatively prime positive integers, then phi of the product uv is equal to the product of phi of u times phi of v. And that is going to be very, very useful. Let's just see examples of how that works out. Oh boy, I just shut this for no reason. Let's go back to where we were. And here we are. Okay, so here we are in, let's say in 2.2 now. So 2.2. So I wonder if I still have that. Yes, phi of 2. That clearly, oops, I don't know how that happened. Phi of 2, phi of 2 equals 1, because 1 is the only number that's relatively prime to 2. And phi of 3, well, that equals 2. Again, these are prime numbers. Oops. So that equals 2. Now, according to our, what about phi of 6? Phi of 6 is, we said before, we gave that example before. Phi of 6 was 2, because it was just the number 1, the number 5. That was, we had that example in the previous, I have it right here actually. Phi of 6 equals 2, which is 1 comma 5. So notice that phi of 6 is equal to phi of 2 times phi of 3. In fact, let's look at some of these other numbers here. Let's look at phi of 9. Now let's see, what do we have? Let's use some examples we have. We have phi of 12. Okay, let's look at phi of 12. Let's go back to where it is. Okay, so phi of 12. Phi of 12. Now, if you recall, we said that phi of 12 was equal to 4. So let's see if we could figure that out. We know that phi of 12 equals 4. So let's take a look here. Well, 12 is equal to 3 times 4. So phi of 3 equals 2, as we said earlier. And phi of 4, we didn't actually, I don't know if we did that one, but let's just do it quickly now. Phi of 4, well, there's kind of two ways we could do it. We could do it based on this formula here, because 4 is 2 to the second power. So we could say that this is equal to 4 times 1 minus a fourth. We say it that way. 1 minus a half, I'm sorry. So we could say that this is 2 to the second power, if you want to get all fancy, times 1 minus 1/2. And that's just, of course, equal to 2. Then again, we could also just say that if we have 1, 2, 3, 4, if we have those numbers right there, let's make them nice and magenta. Look at this color. So, well, 4 is obviously not relatively prime to itself, so that gets. Oops, where are we here? So 4 gets knocked out. 2, it shares a common factor of 2 with 4, so that gets knocked out. And I only have left is 1 and 3. So it makes sense. Anyway, notice that phi of 4 is equal to 2, phi of 3 is equal to 2, and 2 times 2 equals 4. So again, we see an example here that we see here 2 examples. We see that phi of 6. Yeah, this is kind of anecdotal, but this is what I just want to kind of illustrate what the theorem is saying. This is what the theorem is talking about. And of course, we're going to prove this theorem. And so phi of 12 equals phi of 3 times phi of 4. Phi of 3 times phi of 4. I want to make it fit. No, it's not going to fit. All right, so let's just start that involvement. So phi of 12. Let's just put that next line. Oh boy, this is so annoying. So phi of 12 is equal to phi of 3 times phi of 4. So again, this is what that theorem is saying. This is what that theorem is saying. Okay, let's go back to the textbook now. So let's see if we can prove this. Now I'm going to show you the theoretical proof. You'll understand it as well as you understand it. So some of you will understand it more worse. Well, anyway, it is. Then I'm going to show you an example. I'm going to show you an example of an actual number to see what this proof is saying. Let's just run through the actual theoretical proof first. So in order to prove the theorem, we want to look at the number uv, and we want to arrange the number uv in a rectangular array. So we're going to write 1, 2, 3, dot, 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 up to u, and then u plus 1, then start again for the next number, u plus 1, u plus 2, all the way up to 2u, then 2u plus 1, 2u plus 2, dot, dot, up to 3u, and just keep going with that until I get to v minus 1, u plus 1, v minus 1, u plus 2, all the way up to vu. And vu, of course, that's our final number. That's the number that we're, vu and uv is the same, the same thing. So if we look at the, take a random column. So let's look at the first line, 1, 2, 3, dot, 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 all the way up to mu. And let's just take a random number h. H is somewhere between 1 and mu. It's somewhere in this top line. Now, every number in the first line has a factor. I'm sorry, if a number h has a factor in common with mu, then everything on this whole line is going to have a factor in common with mu. Because if h shares a factor with mu, then mu plus h also shares that same factor. 2 mu plus h is going to share that factor all the way down the line. Because let's say there's some number, I don't know, alpha. Alpha is a factor of h, and alpha is a factor of mu. Well, if alpha is a factor of mu, then it's a factor of mu plus h, and it's a factor of 2 mu plus h, and so on and so forth. Anyway, now, on the other hand, on the flip side, if h is relatively prime to mu, meaning there is no common factor, then all of the numbers in this column are also going to be relatively prime to mu. So basically, these columns, it's all or nothing at all. Either the entire column is relatively prime to mu, or the entire column is not relatively prime to mu. So how many columns are relatively prime? How many columns are not relatively prime? Well, the number of columns that are relatively prime depends on how many numbers there are in this first row that are relatively prime to mu. And that by definition is phi of mu. So there are phi of mu columns that are relatively prime to mu, but we're not done there. We want more than that, because we're not looking just for mu, we're looking for UV or VU, whichever way you want to say the same thing. Now, let's look let's look at the numbers in one of these random columns. So we're going to pick a random column here, and let's say we have a random column here, and we want to consider what numbers in these columns are prime now to V. So in this column, in this random column, which numbers or how many numbers are prime to V? So here's what we want to do. So we have mu plus h, 2 mu plus h, dot, 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 all here. So how many of these numbers are in this list, which is the same as I got that list from this column here. How many of these numbers are relatively prime to, I should say, I'm sorry, V? How many relatively prime to V? So we want to write here S mu plus H. Basically, what we're going to show here is that all of these numbers in that column, all the numbers on this list, have different remainders when you divide by V. But we're going to show that in a second. So we're going to write S mu plus H. Let's say that equals QV plus RS. R is the remainder based on whatever S was. So we're doing a division thing here. Now S ranges over all the numbers from 0, 1, 2, 3, all up to V minus 1. And the remainders here are between 0 and V. So clearly S mu plus V plus H is or is not prime to V, as the remainder is or is not prime to V, because I have the V right there. So if the remainder shares a factor with V, then this whole guy, the whole left side shares the factor. If the remainder does not share the factor with V, the left side does not share any factors. So really, that's what's good. Now, notice that all of the numbers RS are different. All of these different remainders, when I go through this process, are going to be different. I'm going to show you this on an actual example. You'll see more clearly. But let's just go through it here. So first, notice that they're all different, because if I have remainder S equals remainder T, that means S mu plus H is equal to QSV plus RS, and T mu plus H is equal to QTV plus RT. And now if I subtract, I get S minus T times mu, because I'm subtracting this equation from that equation. The H's are going to cancel. That I have S minus T times mu. And on the other side, now this is divisible by, and if RS and RT are, this whole thing now is saying if RS and RT are equal to each other, if these two respective remainders are equal to each other, then when I do the subtraction, I have QS minus QT times V. So now I have this guy there as well. So that means that that means that S minus T mu has to be a multiple of V, and the only multiple it could be is 0. So S must equal T. Now, I lost my place. I actually skipped a line, so let me go back to this point right here. So when I do the subtraction, I have S mu minus T mu. That's what I have. That's over here. Here I have QSV minus QTV, because the RS and the RT are supposedly equal. That's what we're doing. We're looking at what happens if they're equal. And that means that S minus T mu is divisible by V. Now that's impossible because, or not impossible, I should say, but mu and V are relatively prime. That was the whole premise. The whole given is that this whole theorem, it works only when u and V are relatively prime. So that was our whole supposition to begin with. Now, the only way it's possible that S minus T times mu can be divisible by V is if S minus T is divisible by V. The only thing is S and T are both less than V, so the only way S minus T is going to be divisible by V is if S minus T equals 0, which would have to mean that S would have to equal T. Now, and that's impossible. Or not necessarily impossible, it just shows that if two remainders are equal, then the two quotient, the S and T have to be equal. So anyway, therefore, no two of the remainders RS could possibly be equal. That's really the point. Now, the remainders RS and V in number are all 0 or positive. They're all, they're not negative. Each is less than V, and they're all distinct. So they must be they must be the numbers 0, 1, 2, 3, all the way up to v minus 1. Must be all those numbers. Obviously be in a different order, but it must be all those different numbers. So it follows that in any column of the array A in which the numbers are prime to mu, there are just phi of v numbers which are prime to v. So in other words, there are phi of u columns. Each column has phi of v. They're phi of mu relatively prime columns, or columns which contain relatively prime numbers to v, and phi of v of them are relatively prime to u, which means v, which is relatively prime to uv. So basically, the number of integers in an array prime to uv is phi of u times phi of v. I got a little garbled up at the end, but that's the point. So the way this, so from the definition of the phi function, it follows that the number of integers in the array A prime to uv is phi of uv. That's the definition of phi of u. So we see that phi of uv is equal to phi of u times phi of v, and it's all beautiful. And that's really the whole argument. There are phi of u columns that are relatively prime to u, and in each column there are phi of v numbers that are relatively prime to v, which means they're going to be relatively prime to uv because everything in the column is relatively prime to u, and it's all going to work out beautifully, and no common factors, and there you go. It's very beautiful. So I want to just show you like an example of this. So I want to look at the number 210. So we're looking at the number 210. I call this phi of 210. That's what I titled this. And 210 is that last number. And we're taking all those numbers here. And we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. I'm going to 15. Oh, by the way, 210 is equal to 15. Let me just note that. Let me make a note of that. That 210 210 is equal to, that's what I'm using here, equals 15 times 16. Okay, kind of using that here. And I'm sorry, times 14, my bad. So that's how we're doing this now. What just happened? Okay, so I'm basically kind of in a way I'm reconstructing the proof. So I'm using an example where uv is equal to 210, and these are my numbers here, 15 and 14. So 1, 2, 3, 4. So here I get 1 through 1 all to 15. Then my next column, it goes 16 to 30, and then it goes 31 to 45. Actually, I want to hide this for a second, just because it might confuse you, and we'll unhide it later. And so on and so forth. Now, if you notice, just look at the top row. The numbers that are relatively prime to 15 are 1, 2, 4, 7, 8, 11, and 13, 14. Those are the numbers on the top column. Those numbers are relatively prime to 15. That means if I take the entire column, so the numbers in the top row that are relatively prime to 15 are 1, 2, 4, 7, 8, 11, 13, and 14, which means each of these columns, all the numbers in these columns are relatively prime to 15. But I don't want just relatively prime to 15. I want to add the restriction that they also have to be relatively prime to 14, well, like really to 14, and 14 times 15 and 210. I really want to add that restriction, which is why it's going to be, which is why the final answer is not just going to be, the final answer is not just going to be, how many numbers, how many columns are there? There are 8 columns, right? So the final number is not just going to be 8 times 14. The final number is going to be smaller than that. So let's look now let's take one column at random. So if we look at one column at random, let me move that back here. Look at one column. I'm going to get rid of myself because it just gets in the way. Okay, that was very profound. So I just took this column. I took column K and I put it over here. So here's the numbers 11, 26. Now 11 is 0 plus 11. 26. I think it'd be better off if I move this column here. Okay, so 11 is 0 plus 11. 26 is 14 plus 12. 41 is 28 plus 13. 56 is 56 plus 0. Now notice I'm writing this as multiples of 14 plus a remainder. 71 is 70 plus 1. 101 is 98 plus this is a multiple of 14 plus a remainder. And now if I just look at the remainders, notice I get, let's see, well, the remainders have to be in a very nice order here. 11, 12, 13, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So you see, the remainders form all the numbers from 0 to 13, all those four numbers. And how many of these remainders are relatively prime to 14? Well, there is 11, 13, 1, 3, 5, and 9, which is 1, 2, 3, which is six different numbers. There are six numbers here that are relatively prime to 14. Now, so this column Q has six different numbers. Now, it doesn't work necessarily that I can go across the board, horizontally. Really, each column is like its own special case, but each column will have the full gamut of 0 to 13 for the remainders distinctly, and it will have in some order or some placement six green boxes which are relatively prime, and that means that there's going to be the number of columns times times 6. And how many columns are there? We said there were 8 columns, so 8 times 6 is 48. So it's going to turn out that phi of it's going to turn out here that phi of 210. Yes, I don't know space insertion. So phi of 210. Oh, guys, I get it. Phi of 210 is going to equal 48. I'll just have to write it. I'll just have to write it this way. Why is it not? It's not letting me type. All right, whatever. It's being annoying now. See, now it's being annoying, so I have to share the annoyance with you. Anyway, let me actually. You know what I'm going to do? Let me just put this in the Google Doc. Let's go back to the Google Doc, and okay, I have to. Well, it's being so annoying here. Why is everything? I feel like the universe. Why is this not working? Okay, everything just froze up. I'm sorry about that. But that's the story. Our page exit the page, and snap. Anyway, phi of 210 winds up being 48, and it's 6 times 8, and that's the story. I'm going to end the video because we did it. Yay! And that's the end of 2.2. We'll see you guys next time. Bye. It's been loads of fun.